Hello everyone. Today we are going to be learning about conic sections for precalculus, and specifically we're going to be learning about parabolas in this video. So to start off, you might have already learned about conic sections last year in Algebra 2. So some of this might be a review, but some of this is newer material too. To start off, conic sections, so when we're talking about shapes that are, or graphs that are conic sections, they're called conic sections because they can be represented as a section of a cone. So for example, here with our circle, the circle can be represented as a slice or the cross section of a cone when we cut it horizontally. So this shape here that we end up with is a circle if we were to look down on that plane that we're cutting it with. For ellipses or ovals, we have an ellipse if we're cutting it at an angle. So a little bit of an angle. That gives us an ellipse. For a parabola, we end up with a parabola if we're at a very specific angle. And specifically, a parabola emerges if we are parallel to the edge. Parallel to edge. So if we're parallel to the edge of the cone, then the cross section that we get is a parabola. Finally, our last shape is a hyperbola, which happens if we keep increasing this angle here. If we keep making it larger, and so 90 degrees, for example, will give us a hyperbola, or extreme angles like that. So here with the hyperbola, we have two sections of it. So we can define these different shapes using sections of a cone. Today, we're going to look a little bit more at the parabola. So we're starting with the parabola, and then we'll look at the ellipse next, and then the hyperbola. All right, so to start off, for parabolas, so we should be familiar with parabolas from algebra. So a parabola we know is, so if I asked you to define a parabola, you might say a parabola is a graph of a quadratic. You might also say a parabola kind of has a U shape. So a parabola facing up, for example, has a U shape. So these are ways to describe parabolas, and parabolas are the graphs that we end up with quadratic equations. We can also define parabolas geometrically. So we can define parabolas just thinking about the points, the set of points that we have in a plane. So define geometrically. So let's write out the definition, and then we'll explain what the different parts of our definition mean. Yeah, what each part means. So a parabola is a set of points in a plane where each point is equidistant to something that we call a focus, so to the focus of the parabola, and the directrix of a parabola. So focus and directrix are new pieces of information about parabolas that we haven't really looked at in algebra, for example, but we're going to look at here because they define the parabola that we're looking at. Okay, and the focus is a point in our plane. The directrix is a line that we have in the plane. So now that we've written out these words, I'm going to draw a quick example to make it a little bit more clear what's happening in this definition. So a parabola we know looks something like this, kind of like a U shape. We have the vertex here. We know the vertex is the lowest or the highest point if it's facing up or down. In other words, the point of inflection where it stops going in one direction, switches to the other direction. We can choose any point on our parabola P. And P is going to be equidistant from the focus. So our focus is a point, for example, here, equidistant to the focus, and the directrix. And the directrix is a line that we have. So for example, down here, this could be the directrix. So every point on this parabola is equidistant from this point. So this is the distance to the focus, df, here, and the directrix. My drawing's not perfect, but imagine those are the same distances. So distance from the directrix, d smaller d. So df is equal to dd. And that's going to be true for any points that we choose. For example, if we chose a point down here, the distance from that point to the focus is exactly the same. We call this A, for example, is exactly the same as that point's distance from the directrix. So this is how we can define parabolas geometrically, as a set of points where they have an equal distance between a specific focus point and a line that we call the directrix. And the focus and the directrix are what define a parabola. So if I give you a focus and a directrix, then there's a unique parabola that matches this definition. Okay, what I want to do next is take a look at the equations that we end up with for parabolas. And we're looking at equations that have to do with this geometric definition. So rather than thinking about quadratics and standard form, we're instead going to be using using equations that give us information about this geometry that we're looking at, like the focus and the directrix. So what I'm going to do right now is write out all of our equations, and then I'll go through and explain them one by one. Okay, so here we have equations for the 4 different directions that we'll see parabolas facing. We have right, left, up, and down. Over here we have the individual equations that we will see for these parabolas. And then from these equations, we can pick out some pieces of information. Specifically, we can find the focus and the directrix really easily with the numbers that we see in these equations. And then finally, for all of these, the vertex is going to be h, comma, k. So looking at our first equation, for example, so here we just have our equation that we would see for the parabola. Oops. Okay, so looking at our first equation, for example, here we would see the equation for our parabola if it was facing right. On one side, we're going to have y minus, and then whatever number we have there is k. That's the y value of our vertex. On the right side, we'll have x minus h. That's going to be the x value of our vertex. And then finally, we'll have a coefficient here where if we take this variable that we're calling a and multiply it by 4, we'll get that number, that coefficient. And the a comes in handy when we look to the right at the focus and the directrix. So the focus is, in this case, going to be the h, so the x value of our vertex plus that a. And then the y value is k. The directrix is the equation of a line, so it's x equals, and then we take that x value of the vertex h and then subtract a. And for all of these, they just switch it up a little bit. For example, when we're looking at up and down, on the left we have x minus h. The x's, notice, are always paired up with the h, and the y's are always paired up with the k. And for all of them, we have a positive or a negative for a as that coefficient in front. So let's take a look at an example given an equation identifying the focus and the directrix and the vertex. Okay, so we're going to take a look at an example problem where we're given some information about our parabola, and our task is to write the equation. So to the right here is the example problem that we're given. Find the equation for a parabola that has a focus at 0, 6 and contains the point 4, 9. So on the left here, I've drawn out a graph of what our parabola might look like. I labeled our focus at 0, 6, and I labeled the point that we know at 4, 9. And our task is to write the equation. What we can do is find those key pieces of information. So find the directrix, find the vertex, and then use those to write our equation. So let's start off. We know that the distance, the geometric definition tells us that the distance between the point and the focus, so this distance here, if we labeled it D, that distance is going to be the same as the distance between that point and the directrix. So this will also be D. This is going to be up and down. So whatever directrix we have down here is going to be D units below that point. So those distances are equal. What we can do to start off is sketch a quick triangle here. So if we think of the triangle formed between the point 0, 6 and 4, 9, draw a quick sketch of what that triangle would look like down here. We have 0, 6 at this point, and we know this point is 4, 9. What we can do is we can find this distance D because it's the hypotenuse of this right triangle. So the horizontal distance here is going to be 4, between 0 and 4. The vertical distance is between 6 and 9. So we have a vertical distance of 3. And then we can use the Pythagorean formula, or Pythagorean theorem to help us out. At this point, we have a 3, 4, 5 triangle. So we would end up with distance of 5. So we know that D is equal to 5 here. So this point is 5 units away from that focus at 0, 6. This tells us that the directrix is going to be 5 units below our point, which if we have a point of 4, 9, 5 units below gives us an equation of y equals 4. Take 9 and subtract 4. So this is our directrix. Okay, great. So we know the focus, we know the directrix. We can also find the vertex because we know that this rule where the distances are equal is also true for any point, including the vertex. So the distance between the vertex and the focus is equal to the distance between the vertex and the directrix. And what we can do is, if these are both D, then we know that this entire distance between the focus and the directrix is 2 times D. So 2 times D is equal to the distance between the focus and the directrix. So 6 minus 4 is 2. So in this case, this distance at the vertex is 1. So this tells us that our vertex is 1 unit below that focus. So our vertex is at 0, 5. In other words, halfway between the focus and the directrix, that point and the line. Okay, great. So if we want to write our equation like we see up here, we have a parabola that is facing up. So we're looking at this row here. We can see our equation is x minus h equals 4a times y minus k. So to start off, we have x minus h, y minus k. X minus the h value of our vertex is 0, so x minus 0 is equal to, and then we have a 4a in front, and then y minus the y value of the vertex is 5. So we can fill out these 2 points. And then the a value we can find looking at either the directrix or the vertex, or sorry, the focus or the directrix. We can see our a value here or here. The a value is just the distance between the vertex and the focus or the directrix. So for example, if we're looking at the focus, so this one right here, we have h comma and then k plus a. So h comma, our k value is 5, so we do 5 plus 1 to get 6. So the a value is that distance that we see between the focus and the vertex, or between the directrix and the vertex. So in front we have 4 times our a value, which is 1. In other words, we get x equals 4 times y minus 5. And the left side is squared. So I think I made a mistake when copying these down, yeah. So the left side on all of these is going to be squared. So we should have squareds all there, all on that left side. Otherwise, we end up with linear equations. So this way we have quadratic equations if we were to expand it. Okay, so our equation here for this problem that we were given is x squared equals 4 times y minus 5. So here's an example of how we can use the geometric definition and the geometric aspects of a parabola to find the equation. We could also do the opposite, given an equation, quickly sketch a graph of our parabola. So we could go into a lot more detail of why these equations are true. I just gave these to you and told them that this information is here, but we don't have a lot of time. So I just wanted to introduce the geometric definition and then go over a quick example of how we can use or work with that definition.